The next one is reduction by hydrogen. So in addition to carbon, hydrogen can also be used as reducing agent. But remember that carbon is used in reducing the less electropositive metal oxides. Then where do we use this hydrogen as the reducing agent? Particularly in the case of tungsten oxide, nickel oxide, indium oxide, etc. type of oxides can be generally reduced with hydrogen to give the corresponding metal. So when we go for WO2 and reduce by hydrogen on heating, this hydrogen combines with oxygen to come out as a water and tungsten becomes free. Thus the metal is liberated with the elimination of water. So here 2H2 and 2H2O. Similarly, when we take nickel oxide NiO and reduce it with hydrogen by heating to give nickel metal and water is formed, which goes off. We also have indium oxide In2O3. When reduced with hydrogen gives indium. The metal becomes free from its oxide and water is lost. Reduction by magnesium. So magnesium is one of the electropositive metals and thereby it can also be used as a reducing agent, particularly in the case of rubidium oxide Rb2O3. So it is an alkali metal oxide Rb2O3. When you reduce it with magnesium metal by heating, this magnesium combines with oxygen to give rubidium Rb. Alkali metal becomes free from its oxide by heating with magnesium, where magnesium is now acting as a reducing agent to give magnesium oxide 3Mg giving 3MgO. So thus magnesium can also be used as a reducing agent, but it is rarely used. Reduction by carbon monoxide, and this carbon monoxide is used as a reducing agent in reducing which oxides of the metal. Already we have discussed that carbon monoxide is one of the good reducing agents in reducing the hematite. So this carbon monoxide is generally formed due to the incomplete combustion of carbon and then act as reducing agent. So we can use this carbon monoxide as earlier studied in reducing hematite Fe2O3, which can be reduced by the carbon monoxide to give iron plus 3CO2. And even ferrous oxide FeO can be reduced with carbon monoxide to give iron plus carbon dioxide. The other two metal oxides which are commonly reduced by this carbon monoxide is one is lead monoxide. Not only can be reduced with coke but also with carbon monoxide to give lead plus carbon dioxide. Cupric oxide CuO can be reduced with carbon monoxide and undergo reduction by it to give copper metal and thereby carbon dioxide. So this carbon dioxide being a gas goes off through the chimney of the furnace, leaving the metals. Thus iron, lead, copper are obtained by reduction with carbon monoxide of their respective metal oxides. And we have another important method called self-reduction process. So what exactly you mean by this self-reduction process, which also is sometimes called auto-reduction or air reduction? That is, no external reducing agent being used during the process. So this is particularly used in the case of sulfide ores of less electropositive metals. Sulfide ores of less electropositive metals. What are the less electropositive metals? These are like lead, copper, mercury. So when we take lead sulfide, galena, copper sulfide, CS, cinnabar, mercuric sulfide, such as these undergo self-reduction. That is, no external reducing agent will be added but can be reduced to give the corresponding metals. But what exactly will happen during this process? So when these sulfide ores of less electropositive metals such as lead sulfide, copper sulfide, mercuric sulfide are heated in air, that's why air reduction, a part of the sulfide ore will be converted into oxide form of it, or sometimes it's sulfate. This oxide form of the lead that is formed, that is PbO, will further react with the lead sulfide on heating to give lead metal directly. So here no external reducing agent being added, we call it as self-reduction process, or we have just heated with air, hence is called air reduction. So in the process, no external reducing agent is added. But what will happen? A part of the sulfide form of the ore will be oxidized to give monoxide, and that will react further with remaining amount of the ore to give the metal. That is, if we take lead sulfide, PBS, galena, when you heat it in air, a part of the sulfide ore is converted into lead monoxide, PbO, and sulfur dioxide. That is 2 PbS plus 3 O2, giving 2 PbO plus 2 SO2. So this PbO formed during the aerial oxidation will now react with the remaining amount of the lead sulfide PbS to give lead metal itself. So lead metal is obtained without using the external reducing agent on heating here, and this sulfur dioxide form goes off. So this is what is the self-reduction process for the extraction of lead from galena. Then let us take cinnabar, mercuric sulfide. This is also sulfide form of the ore. When subjected to treatment with air or oxygen and controlling the temperature, the part of the cinnabar will be converted into mercuric oxide with the formation of sulfur dioxide, and this mercuric oxide formed then combines with the remaining amount of the sulfide to give mercury and sulfur dioxide. Here the temperature is to be controlled, otherwise this mercuric oxide formed is thermally unstable, can directly undergo decomposition to give mercury also. So the balanced equations are 2HgS plus 3O2 giving 2HgO plus 2SO2, and that 2HgO combines with the HgS to give 3Hg plus SO2. So this is what is the method of extraction of mercury from cinnabar. Now what about cuprous sulfide? This is one of the very important ones. Cuprous sulfide, very similar to cinnabar and lead sulfide, galena. It is also undergoes partial oxidation first to give cuprous oxide and sulfur dioxide. It is cuprous sulfide but not cupric sulfide. That's why we get cuprous oxide in the first step. So 2Cu2S gives 2Cu2O plus 2SO2. Therefore, oxygen is 3O2. And this Cu2O form now combines with the remaining amount of Cu2S to give the copper and sulfur dioxide. Thus, extraction of copper is carried out from copper glands Cu2S. And these reactions are generally very important. So, self-reduction is one of the most common methods which are used in the extraction of lead, mercury and copper. The next reducing agent is aluminium metal, reduction by aluminium, and is known as aluminothermic reduction. Now the common reducing agents like carbon, carbon monoxide, hydrogen, etc. are generally not used in the reduction of stable oxides like chromium oxide Cr2O3, manganese oxide Mn2O3, ferric oxide Fe2O3. These stable oxides, as they cannot be reduced by common reducing agents, are all reduced by aluminium. So thereby aluminium is one of the good reducing agents for these oxides to be reduced. As aluminium being more electropositive than chromium in Cr2O3, manganese in Mn2O3, in Fe2O3, this aluminium has got more affinity towards oxygen than for the metal in the metal oxide. So thereby when you take these oxides like Cr2O3 and heat it with aluminium powder, this aluminium which has got more affinity towards the oxygen than for the chromium, aluminium combines with oxygen to give Al2O3 and chromium metal becomes free. So therefore it is 2Al, thereby it is Al2O3 plus 2Cr. And remember that this is one of the highly exothermic reaction. Large amount of heat is liberated, and the amount of heat liberated during the process is more than the temperature used to bring about the reduction reaction. Similarly, when we take the reaction Mn3O4 also can be taken, stable oxide. When this Mn3O4 is reduced by aluminium powder, the alumina Al2O3 is formed, manganese metal becoming free, along with large amount of heat being liberated as expected. So for balancing purpose, we need 3 moles of this and 8 gram atoms of aluminium to give 4 moles of Al2O3, 9 Mn plus heat. Similarly, when we go for Fe2O3 and reduce it with aluminium powder, we'll get Al2O3 plus iron. So therefore, 2Al, Al2O3, 2Fe plus delta H, heat content. And the amount of energy liberated will be about 185 kilocalories. That corresponds to around 3000 degrees centigrade temperature. And this temperature liberated during the aluminothermic reduction keeps the metal obtained in the molten state. And this molten form of the metal obtained, like iron, is allowed to go in the form of drop by drop into the broken parts of the rails. And on cooling, contact takes place and welding can be carried out. So thus, the basic principle involved in Goldsmith's aluminothermic reduction process is this reaction. That is Goldsmith aluminothermic process. So in this Goldsmith's aluminothermic process, a mixture of oxide and aluminium powder known as thermite mixture, where the metallic oxide and aluminium powder are taken in the ratio of 3:1 in a graphite crucible with a small hole cut in at the bottom of it. And this mixture is put in this crucible, which is called thermite, and small amount of aluminium powder and barium peroxide is added. And this barium peroxide is the one which controls the explosive nature of the reaction. And a small magnesium ribbon is embedded in this, which acts as a fuse. And this mixture is all covered by a thick layer of carbon and a thin layer of feldspar to avoid the loss of heat and to protect this mass from oxidation. So what are we going to do? This raw material, what is all there in the crucible already placed, is called charge. This is covered by a thick layer of carbon and a thin layer of feldspar, so that this will prevent the loss of heat by radiation and also the oxidation of this charged raw material placed in the crucible. And now this magnesium ribbon, which acts as a fuse, is lighted. Now what will happen? This magnesium ribbon catches the fire and burns, and giving the intense heat to the mixture. By taking the temperature of this, the mixture starts reacting and causes burning of the mixture. Since the reaction is highly exothermic, as we could see that it is about 3000 degrees centigrade temperature is liberated during the process, and this 3000 degrees centigrade is more than the melting point of the metal iron. So therefore this iron now, which is formed during the reaction, will be in the molten stage, and that will come down in the form of droplets through the small hole cut in the crucible. So this will be allowed to go into the broken rails, and thereby it will, on cooling, contact is made and continuity takes place and welding is said to take place. So this is called thermite welding. That is the reason why this process, Goldsmith's aluminothermic process, is used for welding together the broken pieces of rails, then and there, machinery and parts of ships. The next one is reduction by sodium or calcium or silicon, calcium carbide and water gas. These are some of the reducing agents which can also be used in the metallurgy as reducing agents. Let us see one example for each one of these reducing agents. This sodium or calcium are generally used in reducing the certain metal halides such as titanium tetrachloride. So when we take titanium tetrachloride TiCl4 and reduce it with sodium or calcium, this sodium combines with chlorine to give sodium chloride, leaving titanium. So thus NaCl is formed, 4 moles of it. in the place of sodium potassium can also be used, so that it is TiCl4 plus 4K to give Ti plus 4KCl. So thus alkali metals such as sodium, potassium, calcium, alkaline earth metal can be used in reducing tetrahalides of certain metals like titanium. And magnesium chloride is the one that can be reduced with calcium carbide CaC2 as a reducing agent to give magnesium metal, and calcium chloride and coke becomes the byproducts. And this water gas is the one which is generally used, which is a mixture of carbon monoxide and hydrogen to reduce the nickel oxide. So nickel oxide NiO, as we could see earlier, can be reduced with carbon monoxide to give nickel and carbon dioxide, and the hydrogen associated with the water gas can also reduce this nickel oxide NiO with hydrogen to give water plus nickel. So thus the mixture of carbon monoxide and hydrogen known as water gas can be used in the reduction of nickel oxide to give nickel metal. And silicon can be used as a reducing agent. In the case of, we have MnO.FeO, which can be reduced with silicon and iron oxide to give MnSiO3. The silicate is formed along with iron. So thus here silicon is used as the reducing agent. So thus, in addition to some of the common reducing agents, we can also use alkali metals like sodium, potassium, alkaline earth metal like calcium, and silicon, calcium carbide, water gas also used as the reducing agents.